Neutrinos are very small particles that have no electric charge and almost no mass. They are one of the basic building blocks of matter, and they only interact through the weak force and gravity. They are produced by nuclear reactions in stars, reactors, and other source. 1. Neutrinos are one of the most abundant particles in the universe, but they are very hard to detect because they rarely interact with matter. 1. They can pass through planets, stars, and even people without leaving a trace. 2. Neutrinos have three types or flavors: electron neutrino, muon neutrino, and tau neutrino. 2. Each type is associated with a different charged lepton, electron, muon, or tau. 2. Neutrinos can change from one type to another as they travel, a phenomenon called neutrino oscillation. 3. Neutrinos have very small or zero mass, but they are not massless. 3. The exact masses of neutrinos are unknown, but they are much smaller than the masses of other particles. 3. The mass of neutrinos is one of the biggest mysteries in physics. 4. Neutrinos can help us learn about the inner workings of stars, supernovae, black holes, and other cosmic phenomena. 4. They can also reveal new aspects of the fundamental forces of nature and the origin of matter. Neutrinos are produced by various radioactive decays, such as 1. Beta decay of atomic nuclei or hadrons. 2. Natural nuclear reactions in the core of a star. 3. Artificial nuclear reactions in nuclear reactors, nuclear bombs, or particle accelerators. These processes release neutrinos along with other particles and energy. Neutrinos are very abundant in the universe, but they are hard to detect because they rarely interact with matter. Neutrinos are detected by using very large and sensitive detectors that can capture the traces of the charged particles produced when neutrinos interact with matter. Some of the detection techniques are: 1. Scintillators. These are materials that emit light when charged particles pass through them. 1. The light can be measured by photomultiplier tubes or other devices. 2. Radiochemical methods. These are based on the idea that some atoms can change into different elements when they absorb a neutrino. 2. For example, chlorine can turn into argon when it captures an electron neutrino. 2. The amount of argon can be measured by counting the radioactive decays. 3. Cherenkov detectors. These are large tanks of water or ice that can detect the flashes of light, called Cherenkov radiation, produced by charged particles moving faster than light in the medium. 3. The direction and energy of the particles can be inferred from the shape and intensity of the light. These detectors are usually located deep underground or underwater to shield them from other sources of radiation and noise. What is the difference between neutrinos and electrons? Neutrinos and electrons are both elementary particles that belong to the same group called leptons. However, they have some important differences. 1. Neutrinos have no electric charge, while electrons have a negative charge. 2. Neutrinos have very small or zero mass, while electrons have a mass of about 0.0005 atomic mass units. 3. Neutrinos only interact through the weak force and gravity, while electrons also interact through the electromagnetic force. 4. Neutrinos come in three types: electron neutrino, muon neutrino, and tau neutrino. 4. Each type is associated with a different charged lepton, electron, muon, or tau. 4. Electrons are one type of charged lepton. What is neutrino oscillation? Neutrino oscillation is a quantum mechanical phenomenon in which a neutrino created with a specific lepton flavor, electron, muon, or tau, can later be measured to have a different lepton flavor. This means that neutrinos can change their identity as they travel through space or matter. Neutrino oscillation is a consequence of the fact that neutrinos have mass and that the flavor states are not the same as the mass states. The flavor states are combinations of the mass states, which have different energies and propagate at different speeds. As a result, the flavor states interfere with each other and produce oscillations. Neutrino oscillation depends on the ratio of the distance traveled by the neutrino and its energy. The longer the distance or the lower the energy, the more likely the neutrino will oscillate. Neutrino oscillation also depends on the differences between the masses of the neutrinos and the mixing angles that determine how much each flavor state overlaps with each mass state. How many neutrinos pass through Earth? The number of neutrinos that pass through Earth depends on the source and type of neutrinos. The most common source of neutrinos for us on Earth is the Sun, which produces solar neutrinos by nuclear fusion. At the surface of the Earth, the flux of solar neutrinos is about 65 billion, 6.5 times 10 to the 10 per second per square centimeter. This means that about 100 trillion, 10 to the power of 14, solar neutrinos pass through our bodies every second. Other sources of neutrinos include supernovae, cosmic rays, nuclear reactors, and particle accelerators. These sources produce different types and energies of neutrinos, which have different fluxes and probabilities of interacting with matter. For example, supernova neutrinos are very energetic and can be detected by special detectors on Earth, while cosmic ray neutrinos are very rare and require huge detectors to catch them. Thanks for watching this video. If you enjoyed watching this video, please like and subscribe to my channel.